This is a buffer problem. We can recognize that because we have a weak acid here in acetic acid and its conjugate base, which would be present in solution once this compound dissolves. Okay, we'd also have sodium ions in solution, but we don't care. So we have a weak acid and its conjugate base, a buffer. So we're going to apply Henderson-Hasselbalch, which is pH is equal to pKa plus log of concentration of base to the acid. Alright, the log of the base to the acid reduces down to log of 1 because we have a balanced buffer, and that the concentration of our conjugate base is equal to the concentration of our weak acid. They're both 0.5. So the log of 1, we remind ourselves, is equal to 0. So this whole thing reduces down to 0. And as in the case for all balanced buffers, our pH is equal to pKa, which is the negative log of our Ka, which is 1.8 times 10 to the minus 5. So we get our pH is equal to 4.7447. We want 2 sig figs, 2 sig figs in our answer, and as we only count those decimal places after the sig fig, or after the decimal point, as sig figs, when we calculate the log of a number, our final answer is that the pH is equal to 4.74. Okay, now we could also solve this problem longhand. If we didn't recognize that this was a buffer, or we simply wanted to practice our equilibrium problems. Okay, we'd start with water reacting with our weak acid, and we know that it's going to be in equilibrium with the conjugate base and our hydronium ion. K is the concentration of our conjugate base multiplied by our hydronium ion concentration and our equilibrium concentration of the weak acid. Alright, let's write out our ice table. Initially, both our weak acid and its conjugate base are 0.5 molar. We assume that we're going to lose a little bit of our weak acid. We'll just assume that the reaction goes in the forward direction towards equilibrium. We could be wrong, but that'll come out in our calculations. Assume we don't have any initial hydronium ion concentration. So our equilibrium concentrations, the initial plus a change, 0.5 minus x, x, 0.5 plus x, and x. We can put them into our equilibrium expression. Alright, now to solve this, we're going to use a method of successive approximations. We'll solve for this x, and x is going to be equal to 1.8 times 10 to the minus 5 multiplied by 0.5 minus x and 0.5 plus x. Quantity is on the bottom. Let's, as a starting point, assume x of 0 is equal to 0, and we have x is therefore equal to 1.8 times 10 to the minus 5 for x sub 1. If we took x sub 1, this value, and popped it into our equation, what we would see is that our value does not differ within sig figs. 1.7999, okay, times 10 to the minus 5. So we're done. We have the same number within sig figs, and we note that this is also equal to Ka. So we do have the same final result, that pH is equal to pKa. Because pH is a negative log of H3O+. In this situation, H3O+ is equal to our Ka, 4.7447. Again with two sig figs, pH is equal to 4.74. Okay, so we could solve the problem either way. It's not that much longer going the full bore equilibrium route, but the two methods are equivalent.